Today, every science classroom has a periodic table somewhere in the room. Every general science textbook has one too. But where did all of this information come from? Well, the answer is simple: the gold rush. Not the one in California that the 49ers are named after, and not the one in Alaska, or the one that's on the Discovery Channel right now. Nope, it was the original gold rush. Gold, it turns out, is very important to the development of the periodic table. In fact, the first scientific discovery of an element was done by someone trying to make gold. These men were called alchemists, and yes, they were determined to find a way to turn a cheap, abundant substance into gold, kind of like Rumpelstiltskin and the first gold rush. Now, about a century after the first element is discovered, maybe the most important element to our survival was discovered, almost simultaneously in Sweden and England. In both cases, a compound containing oxygen. Now, water, for example, is a compound made up of oxygen and hydrogen, H2O. This wasn't the compound they were using, it's just an example. The compound was heated until oxygen was released into a tube. This gas, it wasn't called oxygen then, made candles burn brighter, mice became more active, and when it was breathed in by one scientist, he claims his lungs felt lighter. Of course, this makes sense, as oxygen is the gas our body needs, and regular air is mostly nitrogen, which we can't use at all in the air. That's why you see people with oxygen tanks. It's much easier to get oxygen into your body if that's all you're breathing. The discovery of oxygen leads us to the so-called father of modern chemistry, Antoine Lavoisier. Lavoisier did not discover oxygen, but he did name it. Lavoisier, like many of history's famous scientists, had that rare combination of preciseness and disregard for others' feelings and accomplishments that allowed him to rise to fame both in his own lifetime and today. He would read about someone else's work, do it better, and then name his findings. He named 33 elements in all, but didn't actually discover any of them. Not just a scientist, Lavoisier was also a tax collector, which is a pretty unpopular profession in any time, but Lavoisier lived in France during the French Revolution. Yes, he was beheaded. Later, in 1808, John Dalton comes along and publishes a book called A New System of Chemical Philosophy, which introduces the key component in the eventual creation of the periodic table: atomic weight. Dalton argues that each element is made up of tiny particles, atoms, that are the single units of elements. Now, Dalton knows that water is made up of hydrogen and oxygen. He also knows that when water is separated into hydrogen and oxygen, there's 8 times more oxygen than hydrogen released. Hydrogen is the lightest element he knows of. It still is the lightest element today. So Dalton decides to assign it an atomic weight of 1. One atom of hydrogen weighs 1 unit. Now Dalton has to do some guessing. He works on the assumption that nature will always do the simplest thing, so probably 1 atom of hydrogen will combine with 1 unit of oxygen and make 1 water molecule. Since the weight of oxygen released from water is 8 times heavier than the weight of hydrogen, oxygen atoms must weigh 8 units. Great logic, but totally wrong. Luckily, just 1 year later, another scientist does some more experimentation and finds out that 2 volumes of hydrogen combine with just 1 volume of oxygen to make water. So oxygen actually has an atomic weight of 16. By 1816, over 40 elements have now been discovered and named, and scientists were trying to find a way to organize them. The first method used to organize the elements was the law of triads. This law put elements into groups of 3, where the middle element had an atomic weight and density halfway between the first and last element. All 3 elements had very similar chemical properties: magnetic, how they combined with other elements, etc. The trouble with this law was that as new elements were discovered, the triads became groups of 4. Then 5, and, well, you see the problem. So the law of triads was scrapped. The next try was a cylinder where elements with similar properties lined up vertically. It was another solid effort, but didn't work either, as several ions and compounds were included with the elements. So you're starting to get the picture. Someone uses what they know about the elements to create a chart of some kind, and for various reasons, their system doesn't hold up. And that's okay. That's what science is about. Giving it your best shot and then trying again and again and again. Then, in 1869, a Russian scientist, Dmitry Mendeleev, publishes a table that he created using note cards representing the 69 known elements and a version of solitaire he often played. Like his predecessors, Mendeleev organizes his table using atomic weight and chemical properties. Unlike his predecessors, his table was able to show relationships between small groups of elements, like the law of triads, but also all across the table, horizontally, vertically, and diagonally. With this tool, Mendeleev suggests that there are 10 more elements out there that haven't been discovered yet, but he's so confident that they exist, he reserves places in the periodic table for when they are eventually discovered. Out of his 10, 7 are now in your textbook. Looking at the periodic table, we can see the elements are organized by atomic number, not atomic weight. The atomic number tells how many protons are in the nucleus of an atom, something Mendeleev didn't know. The first piece of this last puzzle came when J.J. Thomson discovered the electron. Electrons are not only the tiny particles in atoms, but they're also the moving pieces responsible for electricity. When Thomson was working in 1894, electricity was already a part of everyday life, but no one knew why it worked the way it did. Using electricity in hollow glass tubes, Thomson was studying cathode rays, basically a current of electricity, and came up with the idea that these currents were actually made up of negatively charged, teeny tiny particles found within atoms. Electrons, a negative charge with very little mass. Not long after this, another scientist had a happy accident. He stored some photographic plates, the way people took pictures a while before digital cameras. He was using these for his research in the presence of a compound. He was using these for his research and stored them in the presence of a compound containing uranium. It's important to know that photographic plates undergo a chemical change when exposed to energy from light. This scientist stored his plates in the dark, but when he went to collect them, he saw that they had been exposed. Where did this energy come from? Yeah, the uranium. He had accidentally discovered radioactivity. Radioactivity is when atoms release particles. Another scientist, Ernest Rutherford, was experimenting with these very particles when he discovered one that had the same mass as a hydrogen atom. Remember, 1, but the exact opposite charge as a negative electron. Rutherford had discovered the positive proton. Now, atoms are usually neutral. They don't have a positive or a negative charge, so it wasn't a big jump for scientists to determine that atoms have the same number of protons and electrons. Later, it was one of Rutherford's students, Henry Moseley, who used X-rays to determine the number of protons in each element, and he found that they increased by 1 unit. Hydrogen has 1 proton, helium has 2, and on and on and on. He's the man that numbered the periodic table as you know it today. Who knows what else he may have accomplished had World War I not broken out. He volunteered to be a part of the British Army and was killed in battle before he turned 28. The existence of the neutron wasn't discovered for about 20 more years in the early 1930s. Scientists knew that the atom weighed about twice as much as the protons within it, but they couldn't explain why. Then James Chadwick started bombarding elements with radioactive particles. He found a new particle that didn't have any charge at all. Through lots of math, and further experimentation, he determined it had the same mass as a proton. The neutron was discovered. And finally, the relationship between atomic mass and all of the particles inside the atom made sense. So, that's how the periodic table got into your science book and up on the wall in your science classroom. Aren't you glad you didn't have to figure that out all by yourself?